All right, usual. Let's check on the audio. We're at markers. All right, let's get this one going for y'all. Oh, the other side. Not pan so much. Oh, that's better. All right, so all right. Calculus 2, we are back. So what we're going to look at today, now that you have a good foundation on just what integration is, again, it's basically it's in a reverse derivative. Also corresponds to area and help us find area. But either way you look at it, that's or, just both things. That's what an integral is. So what we want to look at today, I think I mentioned at the last end of the last video, we did some very relatively simple integrals. Hopefully they should be pretty simple to you through those first two homeworks. We did some pretty simple integrals. What do you call it? The last two videos. Now we wanted to look at some more complex integrals. So you'll actually see a lot of the next several videos that we're going to do. Sort of the way it's done in the first half of this class is all about, now that you know what integration is, let's figure out how to do integration as much as possible and in as many circumstances, as many what do you call it? Give me a second. As many types of functions as we can. And once we have it, see, that's actually what you'll see kind of in this class. The midterm, I call it the midterm, I call it the integration test because that is the first half of this class. The purpose is how do you do integration? The second half of this class is how do you apply integration? What can we apply it to? So that little bit that we're doing, so we'll be finding areas under a curve pretty much in every section, but just as like one or two problems. So that whole bit about finding areas, if you think about it, that's an application of integration. It is what integration does, but it's a use of it, right? So we will get a lot more into that in the second half of the class. The rest of kind of this first 2 weeks class is going to be purely how do we do integration. So, like I was saying at the end of the last lecture, what do you call it? We were looking at simple integrals where you saw how it worked forward, so you knew what it was backwards. You didn't even have to really do the integral; you just knew what the answer would have been because you could see the derivative going the other way, right? So today, what we want to focus on, I want to start with the derivative that you guys know. So I want to start with some more complex patterns of derivatives. So the same thing happened when in Cal 1 when you were doing derivatives, right? So at first they started you with some simple patterns. So how to take the derivatives of power functions, how to take the derivatives of trig functions, etc. How to take the derivative of a natural log function, e to the x, etc. So you started with just this function and you basically figured out what the answer would be as a derivative, right? And then what they did is they said, well, unfortunately, not every function is as simple as that. So you're going to have functions that are mixes of these functions, right? So in like a bit like which class is that? No, sorry, different class. But some of those more complex patterns. So when functions are added together, like we talked about in the first couple lectures, then you can just take them piece by piece, right? But some of the more complex patterns, or what about when two functions are multiplied? And you learned a pattern that you call the product rule, right? And what about when two functions are divided? You learn a pattern that you call the quotient rule for derivatives. And what about when one function is kind of stuck in another? It's basically sort of substituted in another, but I think a better way to say it is one function is sort of placed in or stuck in another. And there you learn something called the chain rule. And so today what we want to do is same idea. So we started with simple integrals. Now we're going to go to start doing more complex integrals. And so we want to start looking at some patterns of integrals. And if you think about it, since integrals are the inverse of derivatives, then the patterns for integrals should somehow mirror the patterns for derivatives, just in reverse, right? So there should be some pattern for integrals that's sort of the opposite or the reverse of the product rule. And there should be some pattern for integrals that's sort of the reverse or the opposite of the quotient rule. And there should be some pattern for integrals that's sort of the reverse or the opposite of the chain rule. And drum roll, please. The answer to those questions is yes, in every instance. Exactly because integrals are the inverse, the reverse of derivatives. There is a pattern for integrals that mirrors each of those patterns that you guys solve for derivatives. Product rule, quotient rule, and chain rule just kind of works it in reverse. So today what we're going to look at is the pattern that reverses the chain rule. So actually what I want to start with is I want to give you a problem. I want to give you a derivative that uses the chain rule. And then what we're going to do is start looking at like how would we do that in reverse, right? So that'll be the focus today is how can we reverse the chain rule? So the chain rule gives you a derivative of one function plugged into another. How could we sort of reverse that pattern? Take an integral of sort of one function plugged into another. So let's look at that. So like I said, I want to start with a derivative. Let me see if I can tie it to one of the problems in the exercise. So just give me a second. Which one did I want to do? Yeah, I think I want it to be that one. It's the same thing either way. Same thing. So let's say make sure I read it right. I don't know. Let's say you have the function x squared minus 9 cubed, and I wanted you to take the derivative of this. We want to do d dx of this. So again, going back to your Cal 1 class, this at least, I mean, at least this looks decently simple to begin with because it's just a polynomial. But notice that, so what I've got is, again, I've got this whole thing is cubed, so it's almost like I'm plugging in this x squared minus 9 into this outer structure, this overall structure that is basically thing cubed or x cubed or u cubed or however you want to say that. So I have one function, x squared minus 9, plugged into this outer structure, this outer function that is basically x cubed. And so when I have that, so this is what I was talking about in Cal 1, you realize that I can't just basically do power rule here. I can't just do 3 times this thing squared, because when I take the derivative, I have to account for what's inside the function. I basically have to account for it using the derivative of that function. So I'm going to multiply what I would have done with the power rule on this function by whatever the derivative of x squared minus 9 is. And that was called the chain rule. So that was a pattern you guys learned, and you had to recognize that the function was basically one function inside of another. But once you recognize that, then we take this thing and do, in this case, because it's something cubed, we do the power rule. Then we multiply by the derivative of this. So I want to have you guys do that really quick. So this one, again, we don't even have to pause. Just I'll pace back and forth. But on your side, go ahead and work the derivative of this. All right, let's see what you guys do. So the derivative of this would then be 3 times this thing squared. Again, when you did this in Cal 1, you may have gotten used to basically saying u equals x squared minus 9, and then the derivative of that. If that's the way you got used to writing it, kind of doing it, run with that. What do you call it? Yeah, just the way I do this, I tend to think of those things as objects anyway. So x squared minus 9 is not x squared minus 9 to me, it's an object, it's a thing. So that's why I call it a thing, actually. And that actually helps me process it easier. So I just call it a thing so that I know kind of what to do with it. So this derivative is going to be 3 times thing squared. But then I need to multiply by the derivative of that thing. And what is the derivative of x squared minus 9? That's 2x. So the derivative of this would be 3 times x squared minus 9 squared 2x. Now let's look at the first problem kind of from today. So that's the derivative. So again, think of this as starting with this function, I'm moving down to this function. Integrals are always starting with the bottom function and moving up. So again, the idea today is how do we think about reversing this process? So today I'm going to ask you to do the integral of actually I'm sorry, this is not 10, but let's make this its own problem for the moment. But today I'm going to ask you to do the integral of something like 3 of that exact thing. So if I was going to do the integral of this, squared. And so if I was going to do the integral of this, how would you sort of reverse this process? So the idea is you basically have to realize, or you have to recognize, again, that first of all, this is a function inside of another. Now, what's going to be different about this, or just what's visually going to be slightly jarring at first, compared to when we were doing chain rule, is you have a lot more stuff outside your main piece here, which is x squared minus 9 squared. But the reason you have this stuff outside is that, so again, the question is, how are we going to undo this? So the idea is to undo this, you need to have both a function within another, but you need to have the derivative of that inside function already outside, already present in your integral. So again, you take the derivative, you start with kind of the function, in this case cubed, and then it basically, in some ways, it kind of sheds off these extra pieces that are the derivative of what's inside, 3 times 2x. So if I want to take this in the reverse, if I want to say the integral of this is this function, I've got to make sure that these outside pieces are present, that the derivative of the inside is present. Now, I tend to do this visually myself, so I don't do what they traditionally call U substitution, but the method that we're going to develop here is called substitution, because the idea is basically, if I'm going to integrate this, I've got to pick the function that's inside the other piece, right? So let me show you how they typically write this. U equals x squared minus 9. And in order to integrate this, so all substitution is, they call this the substitution method, but all substitution is reverse chain rule. So I'm going to start with this, and if I have all of this, then when I take the integral, it just moves me back up to x squared minus 9 cubed. So that's maybe the first, hopefully, big or important connection for you guys for this lecture, is that substitution is just reverse chain rule. And in order to pull this off, you have to recognize what function is kind of inside the other function. And then you need to take the derivative of it to make sure that your other pieces, basically the derivative of it's there. So we need to make sure that the derivative that you would multiply by that you'll get out of the chain rule is in fact, is in fact present. So this is u. If I do du dx, what is du dx going to be? Look at that for a second. What is du dx? Good, that's 2x. So that same derivative that we talked about here with the chain. And then what I'm going to do really quick is we'll move that to that side. So what I'm saying here is du is 2x dx. And so this whole piece I can replace with du. So once I have this substitution and the derivative for that substitution, then this whole integral becomes the integral of 3 u squared du. And notice this is a simple integral, indefinite integral, but a simple integral that you can do. So what would the integral of this be? And I'll give you guys a second to do that. Again, I won't pause, but I'll just pace for a little bit and put some music back on it. Why is it deep? All right. So what's the integral of this? Good. So the power goes up to 3, you divide by 3. So the integral of this is just u cubed plus c. And we said u was x squared minus 9. So the answer here is x squared minus 9 cubed plus c. And notice that's exactly what we started with when we did the derivative using the chain rule, except for the c. So substitutions, again, recognizing x squared minus 9 as this function kind of placed in another, and using that as your substitution, all it does is it undoes the chain. Just does the chain rule in reverse. So this whole, every single integral that we're going to do today, by the way, so every single integral we're going to do today is just simply undoing the chain. It's just doing chain rule in reverse. That's all it is. So that's, they make a big deal about substitution in, in a Cal 2 class, but honestly, it's not a huge deal. You don't want to think of it as a huge deal. You want to think of it as something brand new and skippy that you got to figure out. It's just chain rule in reverse. That's all we're doing. So much so that, so like I said, so I mentioned that for chain rule, a lot of you probably got used to writing out the substitution, kind of doing that from writing things that way. So if you did, then this way of writing it will help you. But again, chain rule or substitution is just chain rule in reverse. And so to me, that's hopefully, or so to me, that's so clear that the way that I would actually write this problem doesn't involve u's at all. So even though this method is called substitution, you're doing a u substitution. You're just calling one of your parts u so that you can do your derivative and work out the parts. But the way I would write this, so this is one way to write this. The way that I would write this problem, honestly, is not even that complicated. I would not write any u's at all. So when you're doing this problem, something like this, all you need to do is, again, identify the parts that's being plugged into the larger function, right? So x squared minus 9 is being plugged into this squared power function. And then all you gotta check for is basically, so visually, mentally, you just need to check that you have the rest of the derivative present. So you need the derivative of two x of x squared minus 9. What is the derivative of x squared minus 9? Good, it's 2x or 2x dx if you want to write it. You want to include the dx part. So the derivative of x squared minus 9 is 2x dx, and notice that's present. So once you see that that's present, read on. But once you see that this is present, again, all I'm doing is doing the chain rule in reverse. So in my mind, the way I think about this is I'm thinking about this as the result of a chain rule. So when I do chain rule, what I do is I do the overall derivative and then I multiply by the derivative of what's inside. So when I'm doing this in reverse, when I'm doing substitution as integration, I just want to check off a box. I want to check that derivative is present. And if the derivative is present, then I can just do the integral in reverse like I normally would, right? So since the derivative is present, I'm good. All I got to do is bump this power up to 3 and divide by 3. And so my integral is x squared minus 9 cubed. Put a C on there. And you're great. You got your answer. So I guess what I'm saying is if you're, especially if you're a visual person, you honestly don't really need to write the U's and DU's and stuff like that. You just really don't actually have to write any of that. And if that helps you, because what I've seen is for some students, it actually helps them to write out the U and then write the DU, DX. And if that helps you, it's fine. But I've actually seen for a lot of students that being forced to write the U and do all that stuff actually makes the problem a lot more complicated and longer. And that's because, and that's often because it's just, that's what sometimes when you have too many letters and too many lines of code essentially to get from step A to step B, it just complicates the issue. Makes you think through more than you really need to think through, right? So if something like this is traditionally confusing in the past, what that means is you really shouldn't write the U's. You should do something more like this. All you got to do is conceptually, visually. So if you think like that, you're probably more of a visual thinker. You just got to conceptually, visually check that your derivative is there. Once you've got that, then you just do the regular integral backwards. Or you do the integral backwards from there. Hopefully that connects and makes sense. And we'll practice a ton of these. I even tend to write it more this way though. I'll be honest. For me, I am one of those that even though I know what this notation is doing and what these lines of code and equations are doing, it honestly just complicates the issue way too much. To me, not just derivatives and integrals, but everything in math is actions. It is a diagram on a page, right? So again, the chain rule takes you from this diagram to this diagram, and it takes you down, and there's an action that's happening here. All I need to do in my mind is do this action in reverse. And so everything that I can do, anything that requires me to write another letter and another term and another line of code, is going to tend to complicate that. So what I'm saying is when I'm writing this on the board, in the lecture, I'm going to tend to do something like this. If you need the U's, then I will at least I'll try to mention what the U substitution would be, and you can just check that on your own. So just pause the video, and basically write this part, write down your U, do your D, your DX, try to do that work. You can do that work a little bit on the side of your paper on your own, and just check that works when you get into the same and one fashion. But again, if this confused you before in a Cal 1 class, I'm actually saying you should throw that notation and that way of working through the problem out. And instead of that, you should take a more visual, conceptual approach. So you look at this, you identify what's inside your function, you take the derivative, and maybe you need to do that on paper, or maybe you can do that in your mind. Just check that the derivative is there. As long as that derivative is there, then sometimes literally it's like you're checking that off. It is the chain rule. The chain rule happened and the derivative came out. So because it's there, then I've got what I need to work my way backwards, so I don't even need it. I just take this main part and do the integral, do the backwards to it. So hopefully, again, that connects and makes sense for you. Give you some options as far as how to write this. I'm going to tend to write it this way. Let's do quite a few problems like that. And by the way, this video is going to cover both 5.5 and 5.7 because 5.7, so 5.7 is about taking integrals with natural logs, or integrals that result in natural logs, or integrals that are contained within a natural log, or other integrals that become a natural log, etc. So it's a section about the natural logarithm. But all the problems in the section basically involve substitution. So really, it's just a continuation of this section focusing specifically on natural logarithms. So the work that we're going to do is going to cover you enough so you can do both 5.5 and 5.7. All right. So, like I said, this is what they call substitution. Too many vowels now. All right. So let's work some problems that involve substitution. I want it to be exactly the same. Well, all right, so this is 11 out of your exercises in 5.5. We're in 5.5, this is 11. So we're at 25. Where the integral, the square root 25 minus x squared times negative 2x. So they kind of make it very apparent there what that extra part that you're being multiplied by is. So again, they're making it very apparent this is outside of the square root. So you're embedding to begin with, or at least visually, I hope you kind of connect that when you see that, that should be part of your derivative of whatever is inside. All right, so I want to take the integral. And again, to note, one of the reasons we're doing substitution here, so let's say you get to a test, and I'm just giving you problems to integrate, right? So I'm not saying what section it's from, or what type of integration you need. You're the problem solver, you're the one to figure that out. If you compare this to some of the problems that we just did in the last two sections, notice that there's a lot more going on underneath the square roots. Before, the best you had was maybe like a 5x or something like that, right? But now we have 25 minus x squared. So one of the flags that you might need substitution. And so as we go through some of these, all these sections about integration coming up, I'll tend to do this. I'll try to give you some critical thinking flags and flags for how do I decide which method I'm going to use, right? Because again, when you're doing the homework, you're in the section and you know what method you're using. But on a test, I'm just going to give these all to you in a gaggle, and they're going to be, mixed up. So the first problem is not necessarily going to be a simple integral, and the last problem is not necessarily going to be the most complex integral, right? So you've got to decide as you're looking at it which integral, type of integral I'm doing here, which strategy I'm using for integration. So again, to kind of do a little compare contrast with the past two lectures. Problems from the past two lectures didn't have all this stuff from underneath the square root, and they generally also didn't have anything outside, your main function that you're looking at. So we were looking at square roots, we did cube roots, we did sines and cosines, we did e to the x's. You generally didn't have another thing outside of it. So that's one of the differences you're looking for. You start to see a bunch of busyness going on inside your square root, your e to the x, your sine, your cosine, etc. And or you start to see some stuff outside your square root, your e to the x, your natural log, etc. That means that you're likely looking at a substitution rule. All right, so you look at this. You see busyness inside, you see extra stuff outside, multiplied outside. This is likely a substitution problem. So then your first thing is what's the function that's inside? So what's the function that's inside? obvious question. So I'm not saying it's a dumb question, I'm just saying obvious question. So give the obvious answer. Good, 25 minus x squared. So the first thing, like I was talking about on this last problem, the first thing you want to do in your head, on paper, however you're doing that, is take the derivative of 25 minus x squared. So again, not everybody is this visual thinker, so maybe you have to go to the side here and do that really quick. So you want to do, well, can even, I'll write it using this notation. So I just want to figure out what is the derivative of 25 minus x squared. And what is the derivative of 25 minus x? Yeah, let me see if you guys can see this part of the board too. Really, but it's there. Good. So the derivative of this is negative 2x, negative 2x dx. Notice that is present. Good. So that's the first thing we have to check. Is the derivative of the inside present? Once you have that, then you want to think about what is the outside structure, kind of what's the main function that we're plugging into, and then pretty much how do I do that in? So this is the square roots. So thinking back to the last two lectures, when I have a square root or a cube root or whatever, what do I always do so that I can deal with it in terms of taking the integral? Good, I turn it into an exponent. And you did the same thing in Cal 1. You turned it into an exponent so you could deal with it in terms of a derivative. So what I'm here really in disguised power function. This is the integral 25 minus x squared to the 1/2 power, the negative 2x dx out there. But again, the negative 2x dx is just the result of a chain. That's just a derivative that needs to be present in order for me to work my way back up to what I began with. So that tells me I can go ahead and do the integral of this power function, and I can apply, I could use the pattern that I know for power function. So that means I'm going to take this and add 1 to the power, and if you add 1 to the power, what do you get? Good, you get 3/2. So again, get used to writing these things as fractions because that's our exact answers. So that bumps up to 3/2. And then you divide by 3/2, which essentially flips the fraction. So what does that put? What coefficient does that put out from? The 2/3. So this as an integral is going to be 2/3, 25 minus x squared, 3/2 power, plus c. And you got it. You got the thing. You got 8. That's right. So again, that's, I mean, maybe that feels easy for you or not, but I'm saying that's as easy as it actually. Substitution is just reverse chain rule. As long as you can check that the derivative that you should have there because of the chain rule is there, then in your mind you just work your way back up the ladder. Just work your way back up to what the derivative started with. All right, good. Let's look at another. So the next one we'll look at is 15. So we'll go back and erase some of this. We have x squared minus 2. Hold on. 2x cubed minus 1 to the fourth dx. And they want us to take the integral of that. So again, and a really quick connection to the last lecture. If you don't have limits here, these are indefinite intervals. So your result is a function, right? If we have limits here, then it's a definite integral, and your result is an area, or well, yeah, basically an area. It's a number. So, but we're just looking for indefinite integrals here. So, what function did this start as when you took the derivative? So again, what you want to do is look for, first of all, what function is inside. What function is inside? Good. That's 2x cubed minus 1. And then you want to think about what the derivative of that is. So let's do side here. Let's do a little work. What is the derivative? 2x cubed minus 1. And so hopefully what you're getting here, the derivative of that is 6x squared dx. And notice that if you go back to our integral, we have the dx, we have the x squared, we just don't have the 6. Now so as long as you're just missing a constant or a coefficient, basically, what this means is we can still go forward with this. So we don't quite have all of the derivative. We should have, so one way to think about it is we should have 6 of these x squared dx's, and we only have 1 of them. So what fraction of 6x squared dx do we have here? Good. We have 1/6. So give me a second. This is the thing, I think classically I don't like the way it's normally written in calculus books. So let me either figure out a better way to write it really quick, or write it the way they write it and then kind of connect what's happening here. So give me a second. Yeah. I think one way to think about this then, so like I was saying, we should have 6x squared dx, and we only have x squared dx. We have 1/6 of what we need. So there's a couple ways. I would say too, like if you don't know, you don't necessarily need to write this step, but it is helpful. You can either put the 1/6 outside or inside, but the way that what we're kind of saying here is we have 1/6. So what I'm going to do here is I'm going to put a 6x squared there, which is what we would need it to be. But I can put the 6 there because I'm multiplying by 1/6 out here. So I'm just saying, because 1/6 times 6 is 1, which is what we actually see there. So in some sense, what I'm doing here, so numerically, I'm just pulling a trick, but conceptually, I'm trying to write kind of correctly what we have. We have 1/6 of the derivative that you would get out of the chain rule, right? So the derivative out of the chain rule would be 6x squared, and I only have x squared, I have 1/6 of it. What this does though is, again, now I have my derivative. If I have my derivative, that I can take this and I can integrate it using, in this case, the the rules for power functions, because that's what we have here. Is we essentially have thing to the fourth power. So what that will mean though is I'm going to do all that integration and I'm going to have to tack on the 1/6 to it. So in some sense, just another way conceptually you can think about this is I have the right function, well, just you have 1/6 of what you need. So we're going to do the integral like you had everything you needed, like you had the full derivative, and then just say at the end with it, we have 1/6 of that. That's actually how I think of it. We have 1/6 of it. So again, if it's a constant that you're missing, then I can just adjust with the fraction, basically. So that's essentially how I'm going to do it. I'm going to do the integral. I'm going to use the pattern for power functions and just say at the end that I have 1/6 of it. But if you need a way to write it out that kind of maybe makes sense, kind of justifies it, that this is maybe a better way to write it. Say the better way, but maybe a better way. But either way, what's happening is we have 2x cubed minus 1 to the fourth power. I have the derivative that I would get from the chain rule. So now I just want to work my way back up the chain rule. I just want to take the derivative, the integral of this. So that means I'm going to bump that up to the fifth power, divide by 5. So what I end up with is 1/6 of 2x cubed minus 1 to the fifth. And then I got to divide that by 5. So however you want to write this just depends on how you like to see this fraction work done, or what makes more sense to you with the fraction work. You can write divided by 5 and just realize that now we're going to multiply across. Or you can write it as times 1/5 in the front. Either way, what we end up getting is, so I'm doing 1/6 times this, which is going to make this 30 on the bottom. So I end up getting 2x cubed minus 1 to the fifth power all over 30, or you can write 1/30 plus c, and that's my integral. I will see in some future lectures, future videos, that if you take the derivative of this and what you see here differs from what you see here by more than a constant. When I say more than a constant, I mean there's some extra x's, there's some extra functional pieces with variables in there, then you can't do this. So technically you can do this because, again, if you think back to your Cal 1 class, remember from your Cal 1 class, if you're taking a derivative of some function and that works, you can take the derivative of it. If you multiply that original function by some constant, then the new derivative is just going to be the constant times the old derivative, right? So the constant just follows. And again, the patterns of integrals then should be the same as the patterns for derivatives, just in reverse. So if I'm doing an integral and I multiply it, I multiply it by constants, then the constant just comes down and multiplies by my answer, same as you did for derivatives. But that only works for a constant. So that pattern that you saw with derivatives only works for a constant. So much so, or kind of one of the ways to think about that is in Cal 1, if you took the derivative of the function, you got an answer. Then you started with the original function and multiplied by another function, then you couldn't just multiply the new function by the old derivative. You had to do the product rule. So as soon as you multiply by anything other than a constant, suddenly it's not only is the answer different, the answer is drastically different. You have to do the product rule. You have to do a whole different pattern to get the derivative, right? So the same thing here then. Again, integrals are derivatives in reverse. So if what you see here differs from what you see here by more than a constant, you have some other x to a power, natural log of x, like just some other function of x there, then you can't just drop the piece down. You can only do that with constants. but we can't do that with constants. So again, with derivatives, if you multiply by a constant, you just dropped it down, added it to the derivative. So same with integers. If my difference is constant, then I'm just going to bring that down, multiply it by my integral. All right, so that's my answer. And pretty much honestly, I think we gotta look at we'll look at some more problems that are that are interesting and unique just because of the way they look. They don't look immediately like they're just at best missing a constant. But other than that, it's actually everything in this section and really the next section, but there's some more interesting problems in the next section. But that's actually everything. This is integration by substitution. As long as you know how to do those simple integrals, then all you're doing here is imagining the chain rule, essentially looking for that extra derivative that's being multiplied outside, and then just working your integral in reverse, or working your derivative in reverse, working the integral backwards. So what I'm going to do is let me give you guys a couple of problems for you to work on your own. We'll go over those, and then, like I said, we'll look at some more interesting problems, both from this section and from 570. So what problems are we going to do? Interesting, they don't do anything. Do they have any problems? Oh, there we go. It's like something like that. All right, I think let's do two different, like I said, I put two problems up there, 19 and 23, maybe. Still, I mean, they're making a lot of these sort of. I guess let's do 21 and 23. No, let's do 9. Where is it? Seven x over minus x squared cubed dx 19 and then let's do 21. So sweet. All right, so go ahead and pause on your side, I'll pause on my side. Go ahead and see if you can work your way through both these problems. let's see what you guys did. And I was telling you we were gonna look at some integrals that they all work with substitution, just several of them at least look interesting to begin with. And maybe these looked interesting to begin with for you because the previous integrals that we did, all the stuff was on one line, and suddenly I'm throwing, a fraction in there. And I'm throwing, if you notice on each of these, the main piece really was at the bottom of the fraction. Again, going back to the first two lectures, we kind of saw that, we dealt with, so the types of functions we dealt with polynomials, we dealt with trig functions, we dealt with exponential functions, natural log, we dealt with, rational functions. So just sort of expect that, as we go through each little, not just section, but each little new way of integrating or new tool that we need for integrating some different functions, that you're going to go back and see, so the first thing you expect is you're going to go back and see all those types of functions kind of over and over again. But I admit this does look interesting to begin with. And maybe it didn't look interesting for you and it made sense, but this does look interesting to begin with, right? So there's a couple ways, there's just a couple ways to handle this to begin with. Actually, do I want to drink stuff? Maybe so. You could do this problem either keeping the fraction, or you basically keeping this written as you see it, but kind of like we did in the last two lectures, though, realize that when you have a fraction and there's at least one piece on the, there's one piece on the bottom. So like on the bottom of 23, there's just a square root. There's a bunch of stuff in the square root, but nonetheless, it is a thing with a square, it's a square root of a thing, or something like this. This is a thing to the third power, that you can rewrite these using negative exponents. And so in this case, if you rewrite it with negative exponents, then it actually becomes all on one line. So I'm gonna start it off that way. Each of these problems, I'm gonna rewrite it that way, and you may not have rewritten it that way, but you probably still recognize in your head that it was a negative power. And if you did that, then you're gonna get to the same place I'm gonna get to. You're gonna get to the same answer. One of the things I do want to caution you guys about that is, so I can do that because term on the bottom of the fraction, there's one term on the bottom of the fraction. There isn't this thing plus another thing, etc., or this thing minus another thing. So we're going to see some problems even today, but especially as we go on, where the bottom of the fraction has more than one term. Then we really truly have a proper kind of what I would call rational function. This is a rational function, but we have a real proper rational function where you'll see we can't just do that. We can't just change things to negative powers and go. So when we get to those, we'll look at different ways to handle those problems. But we are lucky in these problems that basically we have one term on the bottom. So for instance, in 19, I can rewrite this as 7x times 1 minus x squared to the negative 3 power dx. And in 23, I can rewrite this as x times 1 minus x squared to the negative 1/2 power dx. And then it just looks a lot easier to deal with, basically. And it looks more like the problems that we just saw. So it just strategically makes it easier for your head to deal with it. It makes it easier for you to deal with. Even if you didn't do this, if you kind of left it, again, if you left it as a fraction, you're still going to play the same game. So for instance, for 19, if you left it as 1 minus x squared to the third power on the bottom, you're still going to think about what's inside and what function's inside, and you're going to take the derivative and compare it to what you have there. And you would be looking at what's on top of the fraction, in this case, to kind of fill what you're missing, right? Or to basically compare it to the derivative that you'll get from the chain rule. So this one, you'll notice that 1 minus x squared is within the square root that's underneath, and so you need to take the derivative of that and compare it to what you see here. So overall, like, your overall process is still the same, but it is easier to see this as negative powers and to work from there. So let's do it that way. All right, so once we're here, again, you want to figure out what's inside. In this case, on 19, it's 1 minus x squared. On both of them, it's 1 minus x squared. But let's pretend we don't see the other problem for a moment. Up here. So I'm going to go ahead and do 1 minus x squared. Take the derivative of that. The derivative of that is negative 2x dx. And so the interesting thing on this one is we have 7x dx. So we have dx, I don't have the x, but instead of negative 2, I have 7. So one way to think about this is that one way to think about this is that I have negative 7/2 of what I need here, which is negative 2x dx. Still kind of don't like this way of writing it, but I think it's helpful for y'all. And I'm just doing this, so I'm just, again, playing a little trick with fractions. The 2's will cancel, the negatives will cancel, and we'll end up with 7 there. So I'm basically, in some ways, I'm just filling in what is the fraction I need here, so that when I multiply it by this negative 2x that I found, I get what I see here, which is 7. And you just got to play a little game with fractions and toss, numerators and denominators cancel. But that would be the constant here that I'm sort of missing. So I have negative 7/2 of this thing that I'm integrating. But once I have that, I have negative 2x, I have dx. So I'm going to take this. Negative 3 is my power, so I'm going to bump that up 1, negative 2, and then I'm going to divide by negative 2. So what I end up with is negative 7/2 1 minus x squared, the negative 2 power. I'm going to divide by negative 2, which then I can multiply through this fraction. What I end up with is 7/4. 2 times 2 is 4. 1 minus x squared to the negative 2 power. Plus c. That is my answer. Now, I'm actually not sure in this homework, so maybe in this homework, so some of the problems they should be fine with you giving a negative exponent, but if they're not, so if you run across some problems where you plug this in, they're saying it's wrong, it's not that you got it wrong, it's just that you got to write it a different way. So sometimes in problems like this, especially when they start you with a fraction, they essentially want the answer to end as a fraction if it needs to be. And if it's a negative 2 power, that means we could rewrite this as a fraction. So what I'm saying is this is my answer, but so is, let's do it down here. So is 7/4 times 1 minus x squared. So I'm basically just taking the negative power there and rewriting it by what it means. It means that 1 minus x squared is on the bottom of the fraction and it's squared. So this is just 2 different ways of writing the same thing. Again, like I've said before, one is Spanish, one is French. So I don't think your homework is going to be picky about which way you write it, but just know that both are possible ways to write it in case your homework is picky. That's your answer. All right, and then we're going to play a similar game over here. So I'm going to take the derivative of 1 minus x squared. Which we know is negative 2x dx. And so what I have here, I have x. I basically am just missing a negative 2. So what I have here is negative 1/2 of the negative 2x that I would need. Lots of parentheses. But now I have the derivative that I need there. So I can take this and do my usual power rule thing. So I'm starting with -1/2. I'm gonna add 1 power, add 1 to that for the power, and if you add 1, what does that give you? Good, that gives you +1/2. And then I'm gonna divide by 1/2, which really means you flip that fraction and multiply, so I'm multiplying by 2. So this is gonna end up being -1/2 times 2 1 minus x squared to the 1/2 power plus c. And 2 times -1/2 is actually just basically the 2's cancel and you get a negative. So this is going to be -1 minus x squared to the 1/2 plus c. And again, I don't think the homework is picky, but just in case it's picky, we have a 1/2 power. So how can we rewrite that? Good, you can write that as a square root. Notice though, this isn't a negative power like the last one was, so you're not gonna write that on the bottom of the fraction. It's just -1/2 means square roots. So square root of 1 minus x squared plus c. And that is another way to write it. Both mean the same thing. This one's just nice because you started with the square root, so it's kind of nice to start with a symbol and see it at the end, right? That's pure aesthetics. It's not mathematics, it's pure aesthetics. But it's just kind of nice. Any things that humans do has a culture to it, right? And humans always create culture. So aesthetics, beauty, even in the most logical thing that we do, there's that is present. All right, good. Very good. Let's look at maybe 1 or 2 more problems out of this section, and then we'll look at some problems out of 5.7. All right, so maybe actually 3 problems. We'll start with number 40. This will be the integral of x sine of x squared, or they usually write it without the parentheses. Sine of x squared dx. So it's understood that if you're taking the sine of x squared, if this was sine squared, they would write it there. So you've seen before. Okay, so let's look at something like this. So again, you'll kind of want to identify what functions is inside another, and notice here it's x squared. So x squared is inside of a sine. And let me move the camera for you. X squared is within the sine. What is the derivative of x squared? So I'm going to start, I won't always write everything here, but the derivative of x squared is 2x. So then what portion, so notice that we have an x and we have a dx, we're missing the 2. So what portion or what fraction would we sort of multiply by to account for that? What portion do we have? Good, we have 1/2. So 1/2 of the 2x sine x squared dx. Again, honestly, if you don't, so the one thing I don't like about this notation, it's just introducing this 2 here, kind of writing these in here. So if you just if you just know from the numbers that you have one half of it, you honestly can just bring it down to your integral. And once if it's the difference is a constant, the constant just follows you to your answer. So if this is weird to you like it is to me to write it this way, go ahead. If this makes a ton of sense for you though, keep writing it this way. But good. So then I have the derivative that I need. So now I'm just doing the integral really of just this function. But again, so x squared is inside of a sine. So I'm really just doing the integral of a sine function. And what is the integral of sine? Think about that. So the integral of sine, when I go back around, that'll get me to negative cosine. So this is 1/2 or negative 1/2 really cosine of x squared. Good. Plus c, and you're done. Um, let's look at 44. Here they do sine of x over cosine of cubed x or cosine of x cubed dx. So again, we're kind of looking at one of these fractions, right? So the first thing is to realize, and you don't have to write it this way, if you just see it in your mind, that's fine. But really what we're dealing with is we're dealing with sine x times cosine of x to the negative third power. Or actually, I'll just write it. Again, this is the way you tend to write it in a pre-calc class or something like that, or maybe even, I'm sure, your last class. I'm going to write it like this, just to be consistent with the way we're writing it for all the other types of functions. But notice then that this is just a power function, and as long as you can make sure it's a power function with cosine in it, so as long as you make sure you have the derivative of cosine, then you can do this integral easily. So let's kind of do these one by one. Let me have you see if you can work the rest of this integral here. So pause on your side, I'll pause on my side. Right, good stuff. So again, what we have inside is cosine. What's the derivative of cosine? The derivative of cosine is negative sine. So notice that yes, it's not matter how to write it. So I kind of almost have what I need, except for I just need negative there, right? So again, like I'm saying, I'm gonna write it with these as a negative negative, just to to show you why it's working or what we need there. But again, that's what we're really saying is here is derivative of cosine is negative sine, so you just need a negative there. So that negative is constant, it'll follow you all the way down. So again, if you just want to write the negative in at the end, then that works just as well. So we have negative of what we need there. Then we got it. That's my derivative. So I can take this and the overall structure is a power function, and I can take the integral. So I'm going to move my power up 1 to -2. I'm going to divide by -2. So what I end up with is then 1/2 cosine of x to the -2 power plus c. Or again, I could write this in fraction form as now 1/2 cosine x squared, or I'm gonna write it that way, cosine squared x plus c. And that is the same thing. That would be our good. And you'll see problems with, again, you'll see all the different types of functions. You'll see some problems with, what do you call it, exponential functions, etc. Same thing. As long as you know how to do the overall integration of those, the backwards derivative on those, then you've got it. You're good. Let me look. I think I want to move to some problems from the next section, but let me just look to see if we need to do one more on this section. Yes, do one. It's 46. It's the integral of plus 1 e to the x squared plus 2x dx. And I think the reason I want to do this one, like I said, you're going to see problems like this with exponentials. It's just because honestly, it just looks freaky. So one of the things I always tell my students in every math class is, don't let the book fake you out, right? Don't let these problems kind of fake you out. This looks hella weird and complex, but you want to approach it the same as all these other problems. So again, I have some sort of main function with something plugged in and things outside. So that tells me that substitution is probably my go here. My main function is sort of e to a power, right? So my main function is an exponential function, but what's being plugged in? The x squared plus 2x. So then you're going to find the derivative of that and compare it to what you see out there, and then kind of work from there. The play is actually exactly the same. So that's one of the things really to get out of this section is as long as you can identify that you're using substitution, the play for substitution is the same every time, which is nice because then it means that you basically get to not trust your eyes. It doesn't matter how crazy these look, and it doesn't matter what combination of functions they are. The whole point of the chain rule, and therefore substitution, working it backwards, is that we can plug whatever function we want into another, and we can still do this work, right? We can still do the derivative using the chain rule. We can still do the integral using substitution. So we really can have some funky, crazy looking stuff with weird functions that you would never think would be plugged into another function. And the play is exactly the same. You're just going to do substitution. So for instance, here what I see is x squared plus 2x is plugged into an exponential function. What is the derivative of x squared plus 2x? Second on that. Good. So that should be 2x plus 2 dx. And notice that 2x plus 2, so I mean, you don't have to factor it, but notice it can be factored as 2 times x plus 1. That is going to be important for this problem. It could be useless for another problem, but it ends up being important for this problem because notice that, so when you take the derivative, you get 2x plus 2 dx, which you see the dx, but you don't see the 2x plus 2 here. But once you factor it, you do see the x plus 1. So you have the dx, you have the x plus 1, you just don't have the 2. So this is 1/2 of what we need. It's 1/2 of the 2 times x plus 1 e to the power dx. But now I see everything. That's my derivative, which means I can just go back and take the derivative of e to a power, or sorry, the integral of e to the power. The derivative of e to a power is e to a power. The integral of e to the power, then going backwards, is simply e to a power. So the integral of this then would be 1/2 e to that same power plus c. And there you go. So looks crazy to begin with. Actually, a relatively sort of simple, maybe not completely simple, but relatively simple. All right, so again, whatever functions they give you, whatever functions they plug into another, you should be able to handle it. Because the process is the same. So let's go to the next section really quick and just look at this in terms of, with basically with natural logs. And by next section, I actually mean 5.7. So not 5.6, but 5.7. Same. It's just not cheating, but that's just incorrect. Hmm. So once here is this. Sure. So something like integral 1/2x+5. Yeah. And when I say familiar, I say familiar because we've seen things like this, like integrate 1/x, or even something like 1/x+5. So this is technically substitution. I kind of say it's substitution light because we'll kind of see it's you basically you almost see the answer to begin with. You don't, at least for me, the way I work through this visually, it's like I almost don't even really need substitution. It's just a small correction there. But anyways, let me show you kind of what I mean. But this is not just simply a 1/x, so we'll treat this as substitution. It is 1 over something, right? So that's what's happening here is you have 2x+5 plugged into an overall 1 over something. So the first thing to realize is you're dealing with a simple rational function, but nonetheless a 1 over function. We know that the integral of 1 over something is natural log. So in fact, we solve separate problems like this first couple lectures. What's being plugged into it is 2x+5. So again, the first thing you want to do is take what's being plugged in and take the derivative so we can figure out what we have and what we're missing. And what is the derivative of 2x+5? Good, it's just 2. So notice that again, we basically have the derivative, it's just this should be a 2 instead of a 1. So I'm just gonna put, or I'm sorry, not a 2 instead of a 1. Yeah, that should be a 2 instead of a 1, so what we need there is a 1/2. So we have 1/2 of what we need. But that's, so we just make, again, we just make a little constant, coefficient adjustment here, and we have exactly what we need. So we have the derivative from the chain rule. So what we have is 1 over this thing. I want to take the integral of that. And the integral of 1 over something is natural log of that thing. So we end up with 1/2 natural log of, and like I mentioned in the last couple lectures, you have to do the absolute value of whatever is underneath. Basically because you're, and remember our domain for natural log is 0 to infinity, not including 0, so it has to be positive numbers. Sorry, not the x. Plus c, and you have here, so 1/2 natural log of the absolute value of 2x plus 5 plus c. That's the integral of 1 over 2x plus 5 dx. So like I said, familiar example, because it basically, it looks like the integral we're trying to do, right? It looks like 1 over something. Good. So let's look at some other integrals that, where you end up using, where, we end up doing the natural log. We end up, yeah, the integral ends up as natural log, or we end up using the natural log in the work we're doing. Let's look at something, let's actually look at time. Nine is the integral x over x squared minus 3 dx. X squared, and I want you to take a look at that for a second. Notice that this does look a lot like, the integrals, several of the integrals that we just did, right? Maybe the only difference is those integrals had a square root on the bottom, or they kind of had this raised to a power, right? But this doesn't have that. It's just x squared minus 3 in the bottom of the fraction. So I'm kind of talking through my process of, looking at that, and basically what I'm doing is I'm trying to see what picture that I've seen before, does this match, or does this, or if it's different from a picture I've seen before, how is it different? Because that'll help you then figure out where we're going with this problem. So the difference here is that, you technically can rewrite this as a power function. So that's what we did with those previous problems. So that's why I'm bringing that up. So the previous problem we wrote it as a power function. But since I don't see the square root or some power here, this thing raised to a power, it's not going to be one of those cases. It's not going to be, you can't integrate this using the power function property. But notice that without the x here, this is kind of 1 over, so it's kind of 1 over something. So, or another way to think about it is this x squared minus 3, since there is no power, it is being raised to the first power, or the -1 power. It is 1 over. So this is structured like 1 over. And so that's actually the overall, structure, the overall function that we're integrating here is a 1 over function. We know the integral of 1 over something is natural log of that something. So that's where we're going with this problem. And so that's what you'll see all throughout the next several examples we're going to do, is as long as it's structured as 1 over something, then that's where we're going. Now, I don't see a 1 up here, I see an x, and that honestly, visually, that is going to, it would throw me off. It's going to throw you off for a second. But realize, so I'm kind of taking this, I'm taking this as 1 over something. The something that I'm plugging in is x squared minus 3. What is the derivative of x squared minus 3? The derivative is 2x dx. So So notice that's actually what this x is about. That just covers the derivative of the x squared minus 3, which would come out when you're doing the derivative of the chain rule. And we don't actually even have 2x, we have 1x, so we have 1/2 of what we need here. So you think of this is 1/2 2x over x squared minus 3 dx. And then we have the pieces that we need there for the derivative. So again, like the last one, this is really just 1 over something. So I can take the integral from there. So not that it'll take you very long to do this, but let me have you do that really quick. So I'll pause on my side, you pause on your side. Go ahead and finish out the integral there. All right, so what you should have gotten here, finishing this out. This is 1 over x squared minus 3, so my integral is going to be 1/2 natural log absolute value of x squared minus 3 dx. Or not dx, not plus c. Is your answer. Let's look at some other problems that, I gotta look at them again. Some of them may, we're gonna see a lot of problems involving fractions here because naturally you can think about it if I'm taking an integral and going up to natural log of x, that means I'm coming from some fraction. So a lot of these problems involve fractions. Let's look at some others that involve natural log in an interesting way. Because let's look at 23. I was like, oh, 23 is the integral natural log of x squared over x dx. So this one, maybe what compare and contrast. What's kind of similar, what's kind of different about this one compared to the others? You kind of shout at the screen. It's just as you think about it. All right, good. So it is a fraction like the others. But notice that the others were just some other function, but they were structured as 1 over. So we knew the integral was going to become natural log. This one's got a whole nother thing going on because this one actually just has the natural log in the function to begin with. And in some ways, it's the reverse because in this one, the natural log is being plugged in. So this one, if you're looking at this, again, you kind of gonna identify what's the overall structure, the overall function, and what's being plugged in. And the weird thing is I do see fraction, but then I see this something squared, and natural log of x is something being plugged in. So natural log of x now is in the reverse role, it's what's being plugged in. It's also just in the integral. And it's being plugged into a power function, but we somehow still also sort of have a fraction going on. So it's kind of, again, so this is a good example too of a problem of like, if you see it and you're kind of understand what's going on, but then there's something weird about it. There's something that doesn't fit a pattern that you've seen before or what you would expect. Sometimes you can't resolve that uncertainty, that kind of like, wait, this is weird and different and I don't know what to do with that. And the thing is, you don't know what to do with that to begin with. Let that uncertainty sit there and basically, so take the process forward and see if some of the process resolve that uncertainty. Not everything is going to look cleanly like something before, but it still may involve the same process or the same concept, concepts and ideas may get you through that weird looking thing, basically. And maybe not. So if you take it forward and it doesn't get you through the weird looking thing, then that really tells you there's something different happening here. But so you'd be surprised that often when there's a weird looking thing going on, you just need to work the process forward. The process will kind of show you why it looks weird and different and maybe not the way it is said. So anyways, so the process is I see natural log of x being plugged into a power function. So I'm going to go ahead and take the derivative of natural log of x and just kind of figure out, hopefully that'll let me know a little bit of what's going on here. So let's take the derivative of natural log of x. And what is the derivative of natural log of x? About that for a second. And shout it out the screen when you got it. Good. The derivative of that is actually 1 over x dx. So notice this over x. That's why this is here. That's actually the derivative that comes out from the chain rule. So this part and this part cover the derivative, which means we don't need to adjust to figure out why they're there or do something with them. It's just that's the derivative. That's the derivative. And that's cool. So that handles that part of substitution that we need. So that checks off, which means all I'm doing really is taking this thing that's squared and doing my integral, which means I'm just doing the pattern for power functions. So I would take this power and add 1, that's going to be 3, then divide by 3. So my answer is going to be the natural log of x to the third power divided by 3 plus c. And that works perfect. So we didn't need to adjust for this x being on the bottom fraction or really figure out why that fraction was there, because it happened in this problem that taking the derivative gave us those extra pieces and weird things that we were looking at. So that's like, in terms of not only math, but just in terms of thinking your way through these problems, in terms of critical thinking and just basically working your way through something that looks unfamiliar. This is actually a really good point to bring up, that often the processes will show you why it looks weird, basically. So let things be weird and uncertain sometimes. It's okay, the process will show you that. And then again, we'll see some future lectures and sections. When the process doesn't show you the weird thing, why it's weird, then that tells you that you need a different process, a different concept, a different way of thought. Good. All right. That was good. That's a cool problem. Give me a second. Let me figure out maybe 2 or 3 other problems we need from this section. Well, at least let me give you this problem. There's the. So we're dealing with so far a lot of polynomials stuck into fractions. Then we had a fun weird natural log stuck into stuff. But overall, you're in this section at least, and again, even if you're on a test and you didn't see this section, when you see this structure of one thing over another, you're hoping, it's not going to be every time, but you're hoping that you can basically get it set up as 1 over something. Or at least so the first guess is the structure is 1 over something. And as long as the derivative complies, then you can work it backwards and do your integrals in natural log. So let me have you try this one. $39. Which way do they do with this? Let's see. So something like this. Secant x over secant x minus 1 dx. Take the end a little bit. Good. Again, notice, so like I was just saying, you have a fraction and you have a bunch of different trig functions going on there. But the hope is maybe I can set this up as 1 over something. And again, we'll see as we go through not just today's lecture, but future lectures, we'll see situations where you can't, and then you've got to figure out what to do. But we're hoping maybe that this up is 1 or something. So let me see if you guys can actually get this just straight out. So can it be set up as 1 over something? What is the something being plugged into the overall 1 over structure? And start there and see if you can get the answer to this. So go ahead and pause on your side. All right, let's see what you got. Again, I think the thing with this is it looks busy. It looks like there's a lot of things going on. But just like kind of the last problem is you want to sort of hope, you want to sort of assume that maybe it's a 1 over thing and hope that the derivative kind of shows you the rest of the stuff that's going on. Because if we do treat this as sort of 1 over, then what's the function that's being plugged in? The interesting thing about this one is it's just secant x minus 1 is the thing that's being plugged in. And what is the derivative of secant x minus 1? It's just the derivative of secant, and remember that the derivative of secant is secant tangent. So notice that now covers everything else that you see. So this is indeed a 1 over function. And what's being plugged in is secant x minus 1. So my integral then is the natural log, absolute value, secant x minus 1 plus c, and that's it. Easy peasy. So again, don't let some of these problems take you out. You're going to see a lot of other things in it. And not every time, but I would say a lot of the times, it's taking the derivative actually catches a lot of the rest of the pieces that you're. All right. Let me see. I don't think we need to do another sort of along that vein. Sure, but that's okay. All right. So now let's go back and look at maybe some, I would say, more interesting problems from this section. All right. Just look at these more interesting problems. Let me prep you with one problem before. So besides all of these, like the last couple problems, all these problems that look crazy to begin with, what we started off with from this section was problems more like the following. 11 for x cubed plus 3. And I got something backwards there. Sorry. Well, maybe not. 4 cubed plus 3. Bye-bye. X to the 4th plus 3x dx. And let me just kind of take you through this problem really quick. So we started with problems more like this, where what's on bottom, so, in this case, again, what's on bottom you want to kind of bet is what's being plugged in. So if I take the derivative of x to the 4th plus 3x, derivative of that is 4x cubed plus 3, and voila, that's exactly what you see on top. Now remember, for a polynomial, when you take the derivative, the powers essentially go down, right? So you take the derivative of the power function, so the powers go down. And that's kind of what we see in the way this problem is presented. The top, the leading power on the top, the degree on the top is less than the degree on the bottom. So if the degree on top is less than the degree on the bottom, there's a really good bet, honestly, that again, like I was mentioning for these last problems, basically, despite how weird the top may look, just assume the bottom is the thing plugging in, take the derivative, and see if that catches the top. And it does in this case. So the whole top is just the derivative that we would get from the chain rule. So this, like the last problem, the answer just ends up being the natural log of x to the fourth plus 3x dx, or plus c. And again, this naturally makes sense. This works because the power on top is less than the power on the bottom. We kind of want the top to be the derivative of the bottom. However, let's look at third. However, we have something like third. Here we have x squared minus 7 on top, or 7x on the bottom. Notice that the power on top now is larger than the power on the bottom. So there's no way that we could basically take the same approach or assume that this is going to be a 1 over function whose integral is natural log, because when you take the derivative at the bottom, you're going to get something smaller, just lesser power, right? So derivative of 7x doesn't go up to x squared, right? Derivative of 7x is just 7. So if the power on top is bigger than the power on the bottom, then we kind of can't assume it's the 1 over structure. Question is, what do we do there? And there's a couple things that'll come up, and it just depends on kind of how this is structured. This one, I want to go back to what I said before about we just have one term on the bottom, right? So we actually saw a problem similar to this in actually one of the last 2 lectures. It's probably in section 5.1. But as long as I have one term on the bottom, I can break this into 2 separate fractions. And so let's see if that's helpful. So we're going to break this into x squared over 7x dx minus the integral, or actually, I guess we don't need to write it as 2 separate ones, but minus 7 over 7x dx. And so the question is, so I can do that. Properties of fractions tells me I can do that. Let me make sure you guys can see that. Barely. Okay, let's turn that. Sure, that works. So I can do that. It's fine enough. But does it help me? And what do you guys think? So looking at this, see anything that we could do there? Just kind of where would you go with this from there? Good. So hopefully you're noticing that you can simplify the fractions. And so that is hopefully a good bet for us. If we can simplify the fractions, then maybe this turns each of these into something that I can deal with for long. So I can simplify those fractions. This one, you cancel out an x, and you end up with what? X over 7. And then now that's just a nice, this is not even a rational function. It's just 1/7 x. That's easy. That's just a power function. And then this one, you end up with 1 over x, but the natural log of 1 over x is, the integral of 1 over x is something I can do. Natural log. So notice that in this case, again, if you have one term on the bottom, try splitting it up into several, the fractions, separate fractions. Because if you can do any simplifying, it likely is going to simplify it into something easy to deal with. So now we can take the integral of this easy peasy. Let me have you guys do that. So pause on your side, I'll pause on my side. Go ahead and take the integral. All right, see what you guys got. So x over 7, the integral on that goes up to x squared divided by 2, so it's actually going to be x squared over 14. And then this one, natural log of x, all this plus c, and we got it. That's your answer. Now that's if there's one term on the bottom. I think I even mentioned in a previous lecture is if there's one term on the bottom, it's just nice because you split it up into separate pieces and it usually works itself out very nicely. However, what if there's more than one term on the bottom? I think I even mentioned it in this lecture earlier that once we have more than one term on the bottom, then we really have to do some work and remember some things. So let's look at, give me a second, I just want to make sure. Well, actually. Is it doing that? That's what I thought. It's not actually. I guess that's because of that. I just don't want to do another wrong. Sorry, taking so long. Well, just something like 7. Integral x squared minus 3x plus 2 over x plus 1. Now I want you to notice again, the power on top is bigger than the power on the bottom, so this is not going to immediately resolve itself in some natural log situation. But again, the difference between this one and the last one is we don't just have one term on the bottom, we have 2 terms. So because of that, I can't just split this up. Yeah, technically you can split it up in separate pieces, but your bottom is going to be x plus 1 on each of them. Basically, we can't just split this up. So what are our other options? And I want you to think back to just a college algebra class. What can we do with something like x squared minus 3x plus 2 divided by x plus 1? So yeah, again, when all your things that have been working so far don't work, you kind of then have to reach back to what's some other process, procedure, tool that I had that would deal with this situation. What we can do in this situation. What do you guys think? So hopefully you're remembering that if I have something like this divided by this, I could actually do long division with polynomials. And I will be the first to say, along with you, that long division with polynomials sucks. But this is one of the reasons it exists is there are some circumstances where you kind of can't do anything but that. That is your tool to get there. So that's what we're kind of what's going to happen here is we actually there's kind of nothing else, no other tool that we can use, but it is one polynomial divided by another, so I can do polynomial long division. So that's what I'm going to start. I'll do some side work here. I'm going to do x plus 1 divided into x squared minus 3x plus 2. And you may not have done this in a while. You may not like to do this. So I will try to assuage both of those things and emotions as we're going through this. So I understand. I don't like to do it either. But like I said, it's just everything that you learn in mathematics, unfortunately, there's a reason that it exists. There are always situations, or you're always going to end up in a situation at some point where you have to use every one of the skills that you've learned at some point. And this is one of the situations where the only way forward is long division. So it sucks, but let's kind of get up on the horse and go and do the thing, right? So to do polynomial long division, first thing I'm looking at is I want to figure out x squared divided by x, or basically x times what gives you x squared. And x times x gives you x squared. And then I'm going to take x and multiply it through here. So x times x plus 1 gives me x squared plus x. And then I'm going to subtract. So then I'm going to do x squared minus x squared. I'm going to do negative 3x minus x. So one of the things I'm going to do here is sort of turn this into a minus. So because I'm subtracting. And again, polynomial long division mimics actual long division. So in actual long division, you divide into the number, or you kind of figure out what you multiply by. Then you multiply. Then you subtract. Whatever you put down here, you subtract from what's above it. So these cancel, and negative 3x minus x is negative 4x. And then in long division, whether you're doing it with polynomials or numbers, you bring down the next piece, next place. So it's negative 4x plus 2. And then I'm going to do this again. So x times what gives me negative 4x? Good, that's negative 4. And then I multiply negative 4 times x plus 1. That'll give me negative 4x minus 4. And then I'm going to subtract these, and subtracting negatives makes them positive. So I'll kind of make these a plus. Those cancel, and what is 2 plus 4? Because that's 6. But then, again, whether I'm doing polynomial long division or the number long division, before you're dealing with decimals, once you have nothing else to bring down, my process is done. So even if I have something left over, it just means that so my remainder is 6, and then over x plus 1 divided by whatever you're dividing by. So x squared minus 3x plus 2 divided by x plus 1 is this. X minus 4 plus 6 over x plus 1. So what I'm going to do is I'm going to rewrite this. I'm going to replace it with all that. But notice kind of what happens here. So again, polynomial long division sucks, but notice that it does transform this into simple pieces that I can easily take an integral from. So whether it's the last problem where you split it up into the fraction up into pieces, or this problem where you're forced to do polynomial long division, either way, the goal, that's actually your goal, which whatever you need in each situation, the point is it should get you, our goal is to rewrite this, to simplify this to something where it's very apparent, very easy to take the integrals of the pieces there. So the polynomial long division sucks, but it does the job. Now these are easy to take the integral. So let me have you guys do that. So go ahead and pause on your side, I'll pause on my side and finish this out. All right, so working the integral here, you should get x squared over 2, or 1/2 x squared minus 4x. And then this is going to be plus 6 times the natural log of x plus 1, absolute value of x plus 1, all plus c, and you've got it. That is your integral. All right, good. And that overall, that should, these kind of scenarios, that'll get you to handle anything that you see in this section 5.7, and also help you going forward to handle a lot of the integrals that you're going to be looking at. So good. So that will get you everything in both 5.5 and 5.7. Again, the main point is substitution. All right. That also ends the lectures for this week, week one. So go ahead and knock out the homework by Sunday night, and I'll see you guys next week for the next set of lectures, 4 settings. All right, catch you guys then.